In this section, we're going to learn about how you use or how you see the exponential growth and decay functions in real life. And a lot of the time when you see the exponential growth and decay functions in the real world, it's having to do with money or the cost of things or putting money into a bank. That's often when you'll see the exponential growth and decay functions. So the first one we have is the exponential growth function. So you'll see this most of the time when we have exponential growth, when things are growing exponentially. So the little a here is your initial principal, how much you initially have. You initially have $500, or there's initially 500 atoms in a biological substance. R stands for the rate, how quickly each year or each cycle is it growing at. It's a percent that you then change into a decimal. So if it grows at a rate of 5%, it would be R would be 0.05. And then T is the number of years, or this could be the number of months. It depends on that rate. So if it grows once a month, then T would be number of months. So you're always going to be substituting into that equation when you have exponential growth. So looking at this first example, it says, since 1900, Franostats production has grown by about 12% per year. They started producing 500 Franostats. How many did they produce in 1920? So what we always want to do first is write down that equation, that exponential growth equation. So the initial amount that they started making was 500. And then it's saying it's growing at a rate of 12% per year. So that's going to be my R, 0.12. And then they want to know how many they produce in 1920. So that's 20 years after 1900. So my T is 20. Then I always add together first what's inside of the parentheses. So I have 1.12 to the 20th. And then I do 1.12 to the 20th in my calculator, and I get 500 times 9.65, about, rounding to 2 decimal places. And then I multiply by the 500 times 9.65. And they'll be producing about 4,823.15 Franostats. Now, you can't produce 0.15 of a Franostat, so you would say they produce 4,823 Franostats as the final answer. Now, here's one that you will see a lot in your lifetime, depositing money into a checking account. All of you will have a checking account or a savings account at some point in your life. And you use that exponential growth equation to determine how much money you'll have if you don't take anything out or add anything into the account, how much money you would have after a certain period of time. So let's say a person deposits $3,000 into a checking account. That's going to be your initial amount. And that account pays 6%. So my R is 0.06. Says how much do you have after 20 years? So this is assuming you don't take anything out of that account or add anything in. So I add together first what's inside of the parentheses, 1.06 to the 20th. Then I do 1.06 to the 20th in my calculator, and I get 3,000 times 3 times 3.21, and then multiply by 3,000, and I get $9,621.41. If I don't touch that money in that bank account at all, that's how much money you would have. So now let's look at how much a gallon of milk is going to cost if it grows at the annual or the yearly inflation rate of 3.1%. Now, milk right now is about $3.29 a gallon. You can find it different prices, different places, but let's say it's about $3.29 a gallon. How much would that gallon of milk, if it goes along with the inflation rate of 3.1%, how much is it going to cost in 10 years, 20 years, and 50 years? So our initial amount is 3.29. It grows at a rate of 3%, so that's 0.031. And our first one we want to do is after 10 years. So first, add together what's inside. So I have 1.031 to the 10th. And then 1.031 to the 10th is 1.357. Then multiply those two together, and in 10 years, a gallon of milk, if it follows the inflation rate, is about 4.46, so $4.46. Now let's do the same thing and find out how much that gallon of milk at $3.29 now, how much about would it cost in 20 years? So all I'm doing is changing that 10 to a 20 and going through the same process. So it starts off at $3.29. The inside, add them together, you get 1.031. Then 1.031 to the 20th power is 1.84. So I have 329 times 1.842. So a gallon of milk, if it continues at that same inflation rate of 3.1%, that gallon of milk will be $6.06 in 20 years. Now let's see how much it would be in 50 years. So it starts off still at $3.29. The inflation rate is still the same, so I'm going to have that 1.031 inside. And now my time is 50 years. So 1.031 to the 50th power is 4.602. And then I multiply those two together, and a gallon of milk, if it follows that inflation rate, would be $15.14 in 50 years. So that's looking at if the value or the price grows over a period of time. Now what if it decreases over time? That's when we see exponential decay. So the value of a car would be an exponential decay. The values go down. The value of the car will go down. You'll see this in science with half-lives of atoms. That's an exponential decay. So the formula looks very similar, except for here we're subtracting the rate instead of adding the rate, because the value or the quantity is decreasing. So if I buy a new car for $20,000 and the value is going to decrease at a rate of 12% per year, what's the value of my car after 5 years? So my initial amount is $20,000. It decreases at a rate of 12% for 5 years. So first I do what's inside the parentheses. So 1 minus 0.12 is 0.88. Then 0.88 to the 5th power is 0.528. And then I multiply that by 20,000. And I get the value of my car after 5 years is about $54.64. So that's if the value is decreasing. The value of the car decreases over a period of time. So that car would only be worth about half its value after 5 years. The last exponential growth or decay function that we're going to look at is when the quantity is compounded continuously. So if you have continuously compounded interest, this is the formula you're going to use. It's P, which is your initial principal, the initial amount. E, that's a number. E is about equal to 2.71. So E actually has the value about 2.71. Then R is your annual rate, and T is the amount of time it's in the account, or the amount of time that it's continuously compounding. A lot of people refer to this as PERT, P-E-R-T, so that they remember that that's how the formula is set up. It's your initial amount, E is a number, and then RT, the rate and the time. So here's an example of using compounded continuously account. So it says, suppose you won a contest at the start of 5th grade that deposited $3,000 in an account that pays 5% annual interest compounded continuously. How much money will you have in the account when you enter high school 4 years later? So assuming you don't take any money out, you don't deposit any other money, how much money is going to be in there? So we use that PERT formula, the initial amount, 3,000. And then again, E is a number. And then our rate is 0.05 and the time is 4. So I always multiply that rate and time together in the exponent. So that's 0.2. Then I do E to that exponent, so E to the 0.2. And if you look on your calculator, you should have an E button somewhere. It's going to look like E to the X, something like that. So look for that on your calculator. E to the 0.2 is equal to 1.221. Then multiply that by 3,000 and you'll get the amount of money that's in your account after 4 years. So you're going to have about $3,664.21 in your account after 4 years without having put anything in or taken anything out. And here's our final example that we're going to do, and we're going to make a little tweak to it as we go through it because there's a typo. So it says, is investing $2,000 in an account that pays 5% annual interest the same as investing, let's change that to 2,000. We're going to invest 2,000 both times at 4% compounded annually. Sorry about that. So we have two different values that we want to look at. We want to look at if I put in 2,000 at 5% compounded continuously, which is that the same as investing 2,000 at 4% annually. So one we're going to use the PERT because it's compounded continuously, and the other one we're going to use the regular equation. So first, let's use that PERT equation. See, the initial amount is 2,000, and we have E. The rate is 0.05, and the time, it doesn't matter what the time is as long as I use the same time on both. So let's use 5 years for this sake. It doesn't matter what it is, just as long as both of the times are going to be the same. So I multiply that 0.05 times 5. So the exponent is 0.25. Then I do E to that exponent. So again, E is a number. It's about equal to 2.71. So E to the 0.25 is 1.284. And when you multiply 2,000 times 1.284, you get 2,568.05. So that's the one that's compounded continuously. Now let's look at the one that's compounded annually. So again, you're going to be depositing $2,000 into the account, so that's my initial amount. Here, since it's compounded annually, I do the 1 plus 0.04, the rate, and then again I want to use the same time, so 5 for 5 years. So you get 1.04 to the 5th. So it's 2,000 times 1.22. And you get $2,433.31. So if I were going to invest, I would pick the one that's compounded continuously because you make about $135 more in that account. So this is how you're going to see exponential growth and decay in the future outside of your Algebra 2 class.